Hello everyone, I'm Greg Weaver. Welcome to the Audio Analyst. Pardon me. Before we delve into today's discussion about amplifier power, I want to thank all of my current subscribers and new viewers for their overwhelming support, as well as all the gracious and kind comments regarding my work here on the channel. It's really moving. I would ask that if you find any merit or value in these conversations, if you enjoy the information I'm sharing here, that you take just a moment to click the subscription and notification buttons. Please don't forget to like and share links to your favorite episodes with your friends, or to leave your comments and questions. I try to respond to every one of them. And should you choose to help me support my efforts, and in the process receive exclusive access and content, you may become a patron by using any of the options linked in the comments section below any of the videos. With a wide range of Patreon subscription levels, I'd like to welcome my newest sustaining Patreon supporter, Thomas Reed. Thank you. You'll be hearing from me soon about your exclusive access. Finally, if a one-time donation makes more sense for you, I've included PayPal and Venmo account info as well. Guys, your support at any level enables me to continue producing these videos and is genuinely appreciated. Now, today we're going to discuss amplifier power and try to clear up some common misconceptions or misunderstandings. Now, electricity is measured in units of power called watts, named for Scottish inventor, mechanical engineer, and chemist James Watt, best known for his improvements to the Newcomen's original 1712 steam engine. A watt is defined as a unit of electrical power and is expressed as 1 ampere under the pressure of 1 volt. Now, the way that amplifier power has been measured and rated in our industry has changed over the years. In my early days in this industry, one of the most popular rating scales was known as IHF, for the Institute of High Fidelity. Now, it typically represented a higher than honest output rating. Most amplifiers can produce considerably more than their effective working power as instantaneous peak power over a terribly short period. IHF peak power was the output power measured over a brief, typically 20 milliseconds, tone burst. There are 1,000 milliseconds in a second, which is some 50 times longer than the measurement burst. So it was totally misleading. It hasn't been used much since the days we affectionately refer to as the time of the Watt Wars, before Bob Carver broke the mold in the early 1970s with his phase linear 700 amplifier, which reliably produced over 350 watts per channel. Today, the standard is the RMS, or root mean square method. It is a mathematical term based on what is effectively the working voltage of your amplifier. Now, we must also understand that power, because it is a measure of work, not a single electrical property like resistance or voltage, is a calculated number, not a measured one. But armed with the combination of any two measurements of voltage, amperage, and/or resistance from our amplifier, we can calculate an amplifier's output voltage, or an amplifier's output in watts. Now again, much like last week's topic on amplifier operational classes and methods, this is such a deep and broad topic that we will keep it very simple. Should you want to learn and understand more about how power, voltage, current, and resistance interrelate, feel free to do further research on your own. But our concerns today will be with understanding how we apply and possibly misunderstand how power is used in our stereo systems and its relationship to the sound pressure levels that our speakers can develop in our listening environments. So let's start with a few simple questions to determine where your understanding levels lie today. Okay? Let's say you have a 100 watt per channel amplifier for your music system, but you just don't feel it plays loudly enough with your floor standing speakers in your fairly large listening room. You've decided that you want to get an amplifier that can play at least twice as loud. How much power should you go shopping for? First question. Or what if you have a pair of loudspeakers that the manufacturer suggests have a useful range of 20 to 200 watts? You are considering using either a vintage 20 watt per channel integrated amp you have sitting in storage, or a vintage unused 350 watt per channel stereo amplifier a family member is willing to donate to you. The integrated will allow the use of its separate preamp output to drive the much more powerful amplifier you've been offered. So, assuming both are in perfectly good working order and are good sounding, well-regarded devices, which one would be less likely to damage and therefore would be better suited to drive these speakers? And why? Question 2. Finally, do you have and use tone controls, the loudness switch or variable loudness contour knob on your receiver or amplifier? Or do you have and use an equalizer? If you do you know how using them will affect your overall power demands? Question 3. So we'll take the answer to that last question first, as the nuances that apply to it will fill in many of the blanks for the other two. The function of tone controls, and an equalizer is nothing more than a multi-band tone control, is to alter the strength or volume of the electrical signal in the bandwidth that it is responsible for adjusting as it makes its way from the program source to the speakers. A bass control alters the strength of a specified range of lower frequencies or tones, and often can affect frequencies as high as 1,000 hertz. While the treble control alters the strength or volume of higher frequencies. But here again, it sometimes starts as low as 1,000 hertz. This signal strength or volume is changed between the pre and power section of your receiver or integrated amp, or by the preamp or line stage of your separate components. A basic understanding of the audio spectrum will be helpful here. This spectrum, for the purposes of our discussion, will be divided into 10 octaves, beginning at 20 hertz, as that is given as the bottom threshold of the range of human hearing, and doubling to form each successive octave. Now, for our purposes here today, the first octave will be defined as containing the frequencies ranging from 20 to 40 hertz. The second octave would then be from 40 to 80 hertz. The third from 80 to 160 hertz, and so on up to the 10th octave, represented as the frequencies from 12,240 hertz to 20,480 hertz. Now, this spectrum covers all the accepted range of human hearing. Below the frequency of 20 hertz, most of us completely lose the sensation of pitch. And we hear, or more accurately, we sense individual bumps of the acoustic pressure wave. Above 15,000 hertz, most of us only get a tingly sensation of irritation at some unheard noise. So, in general, we tend to perceive sounds at the extreme ends of the spectrum rather than hear them. Now, the physics of sound pressure, measured in decibels, can be represented in a logarithmic mathematical fashion, not in a linear one, much like the measurement of light. Instead of increasing in equal increments linearly, with a logarithmic scale, each interval is increased by a factor of the base of the logarithm, typically a base of 10. So, what this means is that to double the volume requires a squaring of the power. As such, the mathematical function of sound pressure reproduction requires that it takes 10 times as much electrical power to reproduce that first octave, the 20 cycles from 20 to 40 hertz, to the same sound pressure level to the human ear as does the 10th octave, the 10,240 cycles between 10,240 hertz and 20,480 hertz. In other words, if a frequency of, say, 12,000 hertz is being played at 10 watts RMS, for us to hear a 30 hertz note at the same volume or sound pressure to our ears as that one at 12,000 hertz, it will demand 100 watts of power. Now, let's apply this to our tone controls. Understanding the logarithmic nature of sound allows us to establish that the lower the frequency, the greater the amount of power is required to reproduce that frequency to a specific sound pressure level. It should now be clear that turning up the bass control is analogous to turning up the volume, albeit only in the specified frequency band affected by that control. But an increase of the bass control from flat to about 1/2 of its full bass boost will typically quadruple the demand for whatever amount of power the amp has been delivering, assuming that it has the reserve power left to do so. Turning the control from full boost or all the way up will typically quadruple the power demand yet again. It now becomes easy to see how an amplifier playing at 5 watts continuous output in its flat position may be asked to develop 80 watts or more with the bass control at full boost. And remember, we've not touched the system volume control throughout this entire process, just the bass contour. So imagine what will happen to a 100 watt amplifier that is playing at 15 watts RMS when someone turns the bass knob to full boost. That amp has just been asked to deliver over 240 watts of power. What will happen when the amplifier tries to meet that demand but has run out of reserve power? So the amplifier will try to deliver what it's asked for, but it simply cannot because of its practical limits, and as a result generates a signal that is grossly distorted. This form of distortion is known as clipping. The output waveform of the amplifier, at up to its full output, normally looks like a smooth and symmetrical sine wave. But when the amp is asked to develop power above its capability, that sine wave loses its smooth curve at the upper and lower maximum voltage swing, or at the rail voltage limits of the amplifier's power supply, and that nice musical and symmetrical sine wave with rounded crests and troughs becomes clipped off, hence the term clipping. This form of distortion is remarkably common with lower output amplifiers, and honestly is responsible for more damage to loudspeakers and amplifiers than any other single cause. This not only may cause permanent damage to your woofer's voice coil by causing it to overheat and open or melt, or by causing your tweeter's voice coil to shoot out of its motor assembly, but it can also cause serious damage to your amplifier through thermal overload. Using tone controls and equalizers, or that single position tone control, the loudness switch, one must take caution not to exceed the amplifier's maximum safe operating power range. An 80 to 100 watt amplifier playing at normal listening volume with the loudness turned on and the bass and treble bumped on to some degree can easily be turned into a several hundred distorted watt monster that can destroy speakers that are rated for even several hundred watts of clean power. Taking clipping distortion just a bit further, turning the volume knob up to its maximum setting will likely produce the same damaging effect. You cannot work under the assumption that since the knob goes all the way around to the stop, that it must be safe. Guys, no amplifier I know of can have the volume knob turned to its maximum clockwise position. Now, the reason a knob will turn past a safe setting is that different sources, optical disc players, DACs, tuners, tape decks, turntables, whatever, have different output voltages. You may have noticed that some pieces of your equipment may play louder or softer than others at the same volume setting on your preamplifier, line stage, integrated amp, or receiver. So the manufacturer of the amp allows you the freedom to adjust the gain as needed. But all too often, they don't take the time to explain the use of the volume control. Now, you all have probably heard clipping distortion before. Bass sounds distorted, often including a cracking type of noise, almost sounding as if the speakers are blown, which they will become if you allow this signal to go to the speakers for any length of time. The sound becomes pinched and rough, grating overall. You may not even be able to put your finger on the reason why you don't like the sound, but you are painfully aware that it is bothersome. Now, understanding the watts to sound pressure relationship is quite useful, as it makes it clear that the actual volume difference between 60 watts and 80 watts, which is barely over 1 decibel, is all but imperceptible to most listeners. But given the direct mathematical interrelationship between power and sound pressure level, we know the following. Doubling the existing power output will achieve a 3 decibel increase in volume. Now, while that increase will be noticeably louder to some listeners, it will not be significantly louder to many. Next, squaring the existing power output will achieve a 10 decibel increase in volume and accomplish a doubling in volume. So now, armed with this information, let's go back to my 2 earlier questions, okay? What was your original answer to my question about selecting an amplifier that would be at least twice as loud as the existing 100 watt per channel amplifier? Don't lie. I'll bet most answered that a 200 watt per channel amplifier would play twice as loudly as the 100 watt per channel amp. We now know that it would require moving to at least 1,000 watts per channel, since we would need a 10 decibel increase or 10 times as much power. What about my question asking which amplifier would be safer to use on speakers the manufacturer has rated as requiring 20 to 200 watts for best operation, a 20 watt per channel or a 300 watt per channel amp? Now, as a bit of an aside, I must tell you that any number of electronics engineers would tell you that a 20 watt per channel amplifier is always clipping. And in some sense, that isn't far from the truth. But the point is that you aren't very likely to ever want or need to turn up the volume on a 350 watt per channel amplifier to achieve any listening level, even a fairly loud one, that would ever drive it past its limit to produce clean power and cause it to clip. However, with a 20 watt per channel amplifier, your need to turn it up to reach a comfortable listening level may well send this smaller amplifier well past its clean output level, driving it into clipping. And since virtually any speakers made today will typically tolerate any reasonable amount of clean, non-clipped output power, even somewhat exceeding their upper listed threshold, As such, the 350 watt per channel amplifier would be the safer, better choice in this question. With that, I'd like to offer my sincere thanks for taking time to drop by and visit today. Remember to subscribe and to like and share your favorite episodes, as well as to post your comments and questions. Guys, please stay safe out there during this COVID-19 pandemic, and definitely keep the music playing. Till next time, cheers.